solution to homework number 6 for ECE 320. This covers H-bridges, DC to DC converters, and Fourier transforms. Now the first problem is at half H-bridge. Calculate the voltages when I have 0, 0, 5, 5, 5, 0, and 5, 5 volts applied to this H-bridge, or half H-bridge. The diode is all important on a transistor. If there's current flow through the diode, you're turning on the transistor. If there's no current flow, it's turned off. So on the first case, 0, 0, I've got no voltage across the diode on the NPN. It's turned off. I've got 5 volts across the PNP diode, so the PNP turns on. When it saturates, you get a 0.2 volt drop, meaning 5 minus 0.2 is 4.8 volts. When I have 5 volts, 0 volts, the PNP is turned off, the NPN is turned off, in which case I just have 2.5 volts and no current flow. When I have 5, 5, the PNP is turned off, again no voltage across the diode, NPN is turned on, and I'm at 0.2 volts. Check to make sure I'm saturated. Beta IB is greater than IC. IB is 4.3 milliamps. If beta is 100, I have 430 milliamps. That's how much current I allow. I'm only trying to push 46 milliamps, so beta IB is more than IC. It's saturated. That checks. In Circuit Lab, I can build the circuits and check my answers. Maybe. So in Circuit Lab, if I build the first case, 0, 0, the PNP is turned on, that's Q2, and what I measure is 4.844 millivolt, or 4.844 volts. I calculated 4.8 volts. The 0.2 volt drops across the transistor is kind of a ballpark guess. It's close to 0, but not quite. That's why we say about 0.2 volts. And it is 5 and 0, both transistors up, and V2 volts, that checks. And when it is 5, 5, the NPN in V2 is 0.2 volts. Circuit Lab actually says it's 0.086 volts. Again, close to not quite. And over here, build a 2.5 volt source with 50 ohms. That's the Thevenin equivalent of 200 ohm resistors. Again, the Thevenin voltage is half of that, 2.5 volts. Thevenin resistance is 100 in parallel with 100, 50 ohms. R5 is just to let me measure current. Something small, just as a test case, test resistor. Homework, please include a photograph so I can tell that you actually did the lab. And notice that the calculated voltage is different than the simulated voltage, is different than the measured voltage. That's typical in this class. You're always going to get 3 different answers. Calculated gives you nice round numbers like 0.20, 0.48, 2.5. Simulated uses a nonlinear model. It won't be exactly 0.20. Measured uses the actual diodes and transistors, which are also nonlinear. Close to the simulated, the Circuit Lab models, but again, everything's got some tolerance. It'll be slightly different. I should get 3 different answers. They'll be close, but slightly different. That's problem 3. On problem 4, we're looking at a DC to DC converter or a buck converter. This is analysis. Given the circuit, find the voltage at V2, both DC and AC. First, find the voltage at V1. If I'm a 75% duty cycle, 75% of the time I'm at 20 volts. The remaining 25% of the time at minus 0.7. That's when the switch opens, current continues to flow, in which case I have a 0.7 volt drop across this diode, making V1 minus 0.7 volts, or 14.825 volts on average, DC. V2 at DC is just 100 over 100 plus 20 times V1. Inductors, capacitors don't matter at DC. Gives you 12.35 volts. The AC portion, V1 is going to chatter. It's going to go between 20 volts and minus 0.7 as the switch opens and closes. So it's 20.7 volts peak to peak, ballpark, at 1 kilohertz. The inductor at 1 kilohertz is 376, J376 ohms, capacitor minus J31 ohms. These in parallel is 9 minus J28. Voltage division, we've done that very many times this semester. So the AC voltage of V2 is the voltage division times the input at 1 kilohertz, gives you the output 1 kilohertz. So what I expect is that V2 is going to be a 12.35 volts constant with a ripple going up and down 1.799 volts peak to peak. And Circuit Lab I can check. If I build the circuit in Circuit Lab, this is actually that switch. The PNP transistors goes over, NPNs go to ground, PNPs go to power. If R3 is to ground, I have this diode is turned on, Q1 saturates, and V1 is 20 minus 0.2, 19.8 volts. If Q2 is turned off, then there's no current flow and the switch is open. To turn on and off Q2, I just use a square wave. This is a PWM signal. Presumably that would be from a function generator, microprocessor, 555 timer. Something sets the pulse width to 75%. If I simulate it, I can now see the voltage at V1, V2, and so V1 is the blue line, and notice it's 20 volts minus about 0.2. That's the 0.2 volt drop across the PNP transistor. That's when the switch is closed. When the switch is open, it's minus 0.7, ballpark. That's V1. V2 then is the orange line. And it's similar to what we calculated. And come back. We calculated 12.35 volts, simulated 12.23 at DC, calculated 1.799 volts peak to peak, simulated 1.64. Again, our calculated off is what I'm assuming is that the input is 1 kilohertz sine wave with an amplitude of 20.7 volts peak to peak. The blue line is not a sine wave. I changed the problem, modified it, so my answer is approximate. So likewise, I'm not surprised that it's different, but it's close. My approximation is actually pretty good. To get more accurate, I throw it in Circuit Lab. Problem 6 is design. Change the circuit so that V2 is 5 volts and 1 volt peak to peak ripple. To get 5 volts at V2, I need 6 volts at V1. To get 6 volts at V1, I need a duty cycle of 6 over the input, 20 plus 0.7, 32.4%. And to find C, a couple ways to do it. One is to use your 5 microfarads from the previous problem as a reference. 5 microfarads gives a 1.64 volt peak to peak ripple at V2. So to get a 0.5 volt ripple, I need the impedance of the capacitor to be 1/3 of, or I need the capacitor to be 64% larger, or 8.2 microfarads. That's one way to do it. There's others. The acid test is throw it in Circuit Lab and see what you get. So in Circuit Lab, changing the duty cycle to 32.4%. Going to set this up so 10 volts is 100%, 0 volts is 0%, 3.24 volts is 32.4% duty cycle. Change the capacitor, and here's what you get. It's close. The DC voltage is 4.88 volts, almost 5 volts, a little bit off because I'm losing 0.2 volts across Q1, so likewise my answer is off by about 0.2 volts. The AC voltage is supposed to be 1 volt peak to peak. It's actually 1.1 volt peak to peak. So that is not quite all the homework. The problem number 8 is Fourier transforms. Our calculations are a little bit wrong. So this is looking at what you have to do to get more accurate. To be more accurate, you put in 10 times more work and get a slightly more accurate answer, which is why I'm not a real fan of doing it this way. But if you want to get more accurate answers, here's how you do it. Fourier transforms isn't really an electronics topic. It's really covered in 343 signals and systems. But this kind of illustrates why you cover it in 343. My input is that blue line, that square wave. It's not a sine wave, meaning it has harmonics. There's a DC term that's just the average. There's a first harmonic, which is twice the average of your signal, that blue line, hit with a 1 kilohertz sine wave, or if you like complex Fourier transforms, complex exponential gives you the cosine term and the sine term. And real part is cosine minus j is sine. That's what's nice about this form is you get both the cosine and sine term in one shot. At 2 kilohertz, find twice the mean of V1 hit with your complex exponential at 2 kilohertz. Gives you cosine, sine term at 3 kilohertz, so on. The reason this is just 3 rather than 3 kilohertz is I made the period 1. I did a change in variable and made the period 1, because 1's a nice number. So if the period is 1, the fundamental is 2 pi. Basically, seconds is not a universal constant. I can make the time scaling on the time axis anything I want. I'm just making it so the period is 1, because I like the number 1. Makes everything easier. Then the fundamental is 2 pi. 2 pi times 2 is the second harmonic. 2 pi times 3 is the third harmonic. Put them all together, and you have an approximation for your square wave taken out to the third harmonic. Once I have the input, I can find the output. And this is exactly what we've been doing throughout the semester. If I have a DC term and a 60 Hertz term, I split it up. I analyze the circuit at DC and 60 Hertz. In this case, I've got a DC term, 12.35 volts, or DC term. At DC, this is the gain times the input, gives you 12.35 volts. The first term is at 1 kilohertz. So here's 1 kilohertz in radians per second. Here's the impedance of the capacitor inductor, the capacitor in parallel with the load, 100 ohm load, the 20 ohm resistor in series with the inductor, voltage division R1 over R1 plus R2, where those are complex numbers, times the input at 1 kilohertz gives you the output at 1 kilohertz. Cosine and sine. Repeat at 2 kilohertz. Recalculate the capacitance, inductance, R1, R2. Output is R1 over R1 plus R2 times the input at 2 kilohertz. Here's the output at 2 kilohertz. Repeat at 3 kilohertz. Here's the output at 3 kilohertz. Put them all together. I've got a DC term plus a 1 kilohertz term, cosine and sine, 2 kilohertz term, cosine and sine, 3 kilohertz term, cosine and sine. Put them all together, and that's what I calculated in MATLAB, which matches up with what I simulated in Circuit Lab. So you can get the same answers. It's 10 times more work using Fourier transforms to get slightly more accurate answers. My preference is solve using approximations. The input is ballpark 20.7 volts peak to peak, and you'll get pretty close. If you want to get more accurate, throw it in Circuit Lab. But if you really want to get more accurate, that's where Fourier transforms come into play. So that is homework number 6 for ECE 320.